So in this video lecture, we turn to one of the more advanced and effective new methods for Markov chain Monte Carlo known as Hamiltonian Monte Carlo, and we'll also talk about convergence. Markov chain Monte Carlo is very nice. It gives us very accurate estimates for even complex probability distributions, but it is also inefficient. It takes a long time to get those accurate answers. So in response, people have developed a number of methods. One of the most effective recent developments is what's known as Hamiltonian Monte Carlo. Hamiltonian Monte Carlo builds on work in physics, as does basic Markov chain Monte Carlo. But what Hamiltonian Monte Carlo does is it uses gradient information for the proposal step. So in addition to just selecting a point based on Markov chain, based on the Metropolis-Hastings criteria, it actually looks at the direction to move in based upon what the gradient is. So in general, we're interested in gradient ascent, so we're looking for movements in direction of steepest ascent. And the gradient gives us that information, and we move in that direction. We accept or reject, however, according to the standard Metropolis-Hastings algorithm, we're just improving the direction of movement for our search steps. So what are the pros and cons of this? Well, quick summary is faster moves to interesting regions. So we're able to much more efficiently search the distribution that we're interested in. And that gives us answers in a much quicker time than we can get with standard Markov chain Monte Carlo. However, it imposes a cost. In order to get that gradient, we have to compute the gradient, so there's additional cost associated with it. And also, it only works for continuous distributions because obviously we can't take a gradient for a discrete distribution. So here's how it works. And you can see the general idea of the steps is much more efficient. We're moving in the direction of the gradient. Obviously, we're still going to search occasionally in directions that are not directly up because we want to search the whole distribution, but nonetheless, we search more efficiently than we would in Markov chain Monte Carlo because we're using the gradient to help inform our search. Okay, now let's talk about convergence diagnostics. Well, the Markov chain, as we know from the basic theorem that we saw for Markov chains, is going to eventually converge to the limiting probability distributions for that Markov chain, and those, in fact, are going to be equivalent to the target distribution that we're interested in. So that's all great. The problem is how long it's going to take, and that's the issue of convergence. Unfortunately, there's no provable guarantee that it will converge in the sense that we don't know in finite time it'll converge. We know in infinite time it'll converge, but we don't know. That's not going to do us much good. We want to know when it'll converge in finite time. Now, in fact, in most real applications, it converges, obviously in finite time. But the question is, how long do we have to let things run in order to get to that convergence, in order to get to a good answer? And what we typically do is we use some tests to help us decide if the chain has converged to our desired target distribution. The most common things that we use are what are called trace plots. And trace plots plot the value of the draw versus the iteration number. And they show how well the chain is sampling or mixing the parameter space. So that's the kind of trace plots are by far and away the most commonly used way for us to judge convergence. They really show if the chain has gotten stuck in an area of the sample space. And we typically make a trace plot for every parameter that we're looking at in a probability distribution. So this gives us a good sense of how well we're converging with regard to that distribution by looking at every parameter. We also look at density plots. These don't really tell us whether or not the quality of the convergence, but they do tell us how the sampling is progressing. And in fact, many distributions will have skew in them, but that skew should be as a result of the problem and not because of the chain having problems in converging. And here's some examples of what these look like. we have on the left, we have the density plots, and on the right, we have the trace plots. And in this particular example, we have two parameters that are in fact skewed, and we can see that in the density plots. They have skew in them. And however, two others are pretty much symmetric, and that's nice. But the ones with skew have skew because they're supposed to have skew. They're supposed to be bounded below by 0 in this particular case, and therefore they're supposed to be skewed. So the fact that they're skewed is okay. And when we look in the trace plots, we can see that skew. Now, I should point out that these are actually trace plots that are of 4 runs. The nice thing about Markov chain Monte Carlo is that it allows for embarrassingly parallel calculation. So in other words, we can run each one of these chains on as many processors as we have. And in this particular case, we've in each one of these, we've run it on 4 cores. So you can see that there's 4 runs of exactly the same thing. Of each parameter, we're looking at the Markov chain Monte Carlo estimates. In this case, we're looking actually at the Hamiltonian Monte Carlo estimates for each of these parameters. Okay, we're looking at the trace of that. And these trace plots show good convergence. This is what we want to see. There's no indication that there's lack of convergence. Every one of them, even the ones obviously that are skewed, they're still showing good convergence, the kind of behavior that we would like to see from the chains, showing that they're converging to the underlying distribution. So we'd be confident that we've got good, accurate representations of the distribution based upon the traces for these parameters from that distribution. So in addition to graphical methods for diagnosing the convergence of our chains, we can also use analytics. And here we'll talk about the most popular of these analytics. And the way that we compute this analytic is that we start with the variance within a chain. So we look at each one of the chains that we run. And in the previous example, we had 4 chains, each run on a different core of our computer. And then we compute the variance within each one of those chains. And we call that the within chain variance. The between chain variance for these M chains, again, our example had 4 of some length, capital N, is computed in the following way. We first compute the average for each one of the chains. And the average is over the particular parameter or variable that we're interested in. For example, we're showing here as theta, and the theta could be a parameter from a beta, it could be a parameter from a binomial, it could be one of the parameters in a multinomial or in a Dirichlet. It could even be, for instance, a coefficient in a regression. Regardless, it's the value that we're computing in that chain, the value that we're running this Markov chain Monte Carlo in order to estimate. So we compute the average over that chain, and that's shown by this average formula. And the average then is shown as theta bar j, where j is the particular chain. So in our example, it'd be one of the 1 through 4. Okay, so we had 4 of them. So j would be 1, for instance. And the bar indicates that we've taken the average, and that's what that formula is. Okay, and then we compute the average of each one of those averages, and that's just summing them up and dividing by m, and in our case, m is 4. So with those two, we have theta bar and theta double bar. Well, then we just compute the difference, the squared difference between them over each one of the chains, dividing by m minus 1, which gives us the sample standard deviation. Then we multiply it by n, and you'll see why in just a minute, because we're actually going to cancel that n out, because what we've done is we've computed this sample average, we've given it a weighting, and now we're going to compute the overall variance as a weighting between the within and the between. So this is our estimate for the variance of the chain for this particular parameter. And when we look at it, the formula, we see that we give the between variance a weighting of 1 over n. And if you look at the formula for the between, it's multiplied by n, so that cancels out. So basically, we're just computing the variance, the estimated variance between the chains. The within, we're giving a weighting of 1 minus 1 over n. And if n is large, and it typically is, and there's a lot of weighting going into that particular value. So the within should be pretty close to 1. And the question is, how much is the between contributing? Well, this is what's measured then, is the shrinkage factor. So the shrinkage factor or scale reduction factor is just the square root of this estimated weighted variance that we just computed divided by W. And as we said, that should be pretty close to W if the between is pretty close to W. And if it's not, then in fact this will be larger. It'll be a value much greater than 1. So that's what we're looking for, is how much greater than 1 it is. And the rule of thumb is that if it's greater than 1.2, you should run your chains longer because they're not converging. The between variance is much bigger than it should be. It's much different from the within variance, and that's suggesting that there's some deviation in the way that these chains are running and they're not converged. So the shrinkage factor is attempting to capture that particular aspect and diagnose whether or not we have convergence through that analytic. Okay, so let's look at a quick summary of what we found from these sampling methods. The first thing to note is that sampling is a very accurate way for us to go after the problem of modeling complex probability distributions for Bayesian machine learning. Of all the methods we have, this method, sampling, provides us with the most accurate representations of these complex distributions that we can get. If you can't get a closed form solution, which you can't except for very simple and typically non-realistic problems, then sampling is the way to go. So sampling is the approach that we use for most real problems where we need good accuracy. It also, as indicated, it'll handle the complexity of these difficult probability distributions. The problem is that it's slow. And the result of being slow is that it doesn't scale well to really big data problems. And that's an issue. So we've got good accuracy, ability to handle complexity, but unfortunately it's slow and it doesn't scale as well. We should point out that there are new sampling methods that are coming out all the time. So you should keep informed as professional data scientists as these come out. Because the good news is that people continue to improve. The Hamiltonian method that I gave you is relatively new, but it's still on the order of 20 years old. And we're looking at newer methods that have come out since. In fact, many people have implemented, what's happened is many people have implemented this Hamiltonian Monte Carlo method in a much more effective way. So we're seeing that kind of thing happening all the time. There are also methods that use what's called tempering, and they basically use an adaptive approach to the search over the distribution or the space of the target distribution that we're looking for, so that areas of low probability, they search in less, they find that, they adapt, and they move quickly away from those to areas that we're much more interested in. So there are adaptive methods, tempering methods that people have come up with as well. And this is occurring all the time. There's a lot of interest in this because we do have a very accurate method, and the question is, how do we make it more efficient and effective for these real problems?